Welcome to our video blog about bridging static and dynamic analysis using Lastline process snapshotting. In this video, we're going to show how to use Lastline's process snapshot feature on a CryptoWall sample. We've already written a detailed blog post on CryptoWall, which you can read by visiting the Lastline Labs blog. To begin, let's search for CryptoWall samples in our intelligence database. Lastline's intelligence platform provides multiple ways to search for relevant samples. For example, one can search based on dynamic behavior, external antivirus information, particular IP addresses or domains, etc. In this case, we're going to search for samples using simple labels. As can be seen, the system lists all the samples classified under the same name, and it also shows the top hosts and IP addresses contacted. Let's open the latest analyzed sample and switch to Overview. The overview shows all the detections from our full system analysis sandbox. Now let's switch to the details of the Windows XP analysis report. It can be seen in the report that there are multiple analysis subjects and that the second subject is explorer.exe, which is started because remote data is injected. Lastline process snapshots are very handy in these scenarios, as one can directly view the injected code in IDA Pro instead of manually analyzing and extracting the injected code. For more information on process dumps, you can click on the question mark next to Process Snapshots. This will take you to the Process Snapshot wiki page, which provides instructions to set up process snapshots in IDA Pro. We already have everything set up, so we simply download the process snapshot for subject 2, that is, explorer.exe, and load it into IDA Pro. Upon loading the snapshot, IDA Pro recognizes it as a Lastline process snapshot and asks which snapshot needs to be loaded. In our sandbox, we take multiple snapshots at interesting points, such as execution from untrusted memory, process creation from untrusted memory, etc. Let's select the first one here, that is, execution from untrusted memory. A snapshot of this kind often points to injected code. Now that the snapshot is loaded in IDA Pro, we can examine the injected code. After some reversing, we can confirm that this is indeed injected code. We reversed and renamed some functions. Let's look into some of the reversed functions and see what they look like. For example, let's look into proc persistence cleanup. As is obvious from the name, this function is used for persistence. If we look deeper, we will see that the main malware executable path is passed as an argument to the persistence function, and later its process is terminated and the main file is deleted. Now let's look at disable backup restore. This function is responsible for disabling backup and deleting restore points. If we go inside the function, we can see that first it resolves function srRemoveRestorePoint, which is used to remove the restore point, and later calls it 1,000 times to delete the first 1,000 restore points. If we go down, we can see how it disables the system restore using the registry. If we go down further, we see how it executes vssadmin.exe with the argument necessary to delete the shadow volume copies. This is the process snapshot from servicehost.exe. We've already analyzed some of the interesting functions inside servicehost.exe. Here we can see that first it resolves imports and then decrypts its network configuration. Finally, it enters into a loop and tries to connect to its command and control host. The sample will encrypt the files if it gets the expected response. Let's see how the malware decrypts its network configuration. We already identified the function, which we call proc decrypt network servers. The function internally calls the proc decrypt c function and passes the network config structure as a parameter. As we already described in the blog post, the first part of the network config structure is the RC4 key, followed by the size of the data and the encrypted data itself. If we explore the proc decrypt function, we can see the invocation of the proc RC4 decrypt function, and then later the call to proc decompress. If we explore the proc decompress function in detail, we can see that it calls the RTI decompress function. Since we have all the encrypted data in the snapshot, and we know the decryption key, we made an IDA Python script to automate the decryption process. The script then gets the data from the defined locations and then applies RC4 decryption and decompression on the data. Let's execute this IDA Python script in the process snapshot. As can be seen in the IDA Python window, it successfully decrypted CNC configuration data, such as the URLs to contact for downloading commands.